Hello chemistry students, and welcome to the 5.04 teaching video on gas stoichiometry. In this video we're going to be covering all the topics in lesson 5.04, and let's go ahead and get right into it here. First, I just want to take a moment and mention the standards that we are going to be covering as we go through this lesson. The first one is that we're going to follow precisely a complex multi-step procedure when carrying out experiments, taking measurements, or performing technical tasks. Analyze the specific results based on explanation in the text. Secondly, we're going to use units as a way to understand problems and to guide the solution of multi-step problems. Choose and interpret units consistently in formulas. And then finally, we're going to apply the mole concept and the law of conservation of mass to calculate quantities of chemicals participating in reactions. Now, specific to this lesson, our objectives are going to be to apply gas laws and stoichiometry to predict the outcomes of chemical reactions. So let's go ahead and get right into that then. All right. To do this lesson, you do need to make sure you have some mastery of previous lessons. First, 106, 4.02, and 4.06. In 1.06, we worked with unit conversions. 4.2 is balancing equations, and 4.6 is stoichiometry. All three of these lessons are vital to have success in 5.04. If you need to brush up on them, please go back and review those lessons. You can watch the videos or go back to the lesson itself. But make sure you have those down before you attempt 504. And you also need 506 complete, dealing with the gas laws, knowing the different variables that are involved there. Alright, so again, just to reemphasize, if you have not mastered those lessons, please go back and review those. Otherwise, a lot of 504 will not make sense. You need to have a good background before you do this lesson. Alright, so no further ado, let's get into them here. Stoichiometry, using the ideal gas law. Alright, basically we're taking what we learned in Module 4 and what we learned in Module 3, or excuse me, in 5.03, and we're kind of combining it all together. Alright, and basically if you're given volume, pressure, and temperature of a gaseous reaction, then you can use the ideal gas law to figure out the moles. Back in Module 4, you were typically given the grams, and you had to convert that to moles, and then you were able to solve the problem. Well, to do that, we have to use, again, the ideal gas law, which is written right here. N equals PV divided by nRT. Now, the more common version that you've probably seen is PV equals nRT. Either of those is an acceptable format, and basically all it is just rearranging the formula depending on what we're solving for. So in the version that we saw here first, because we're solving for the number of moles, that's why we rearranged it PV divided by RT. And you can see over here, to get N by itself, I would simply divide both sides by R and T, and that would get me N by itself. So again, back from 503, just to recap, N is the number of moles, P is pressure, and it always has to be in atmospheres, V is volume, always has to be in liters. R is the ideal gas constant, and that number is always going to be 0.0821. And then finally the T, which I apologize, forgot to put that on here, so let's add that in. T is temperature in Kelvin. Alright, so the hard part really a lot of times is just making sure you got everything in the correct units. Once we have everything in the correct units, then it's just a matter of plugging into the formula and solving for what we need. Alright, so that's the first part of this that we're going to use. The second part is the stoichiometry. And again, stoichiometry is a process that we are able to use in a mathematical sense to do conversions and calculations to determine the relationships between the reactants and products in a chemical reaction. Now, back in 406, in lesson 406, you learned that there's basically a three-step process when you do stoichiometry. You first take what you're given, and you got to convert it to moles. That's always the first thing. The second thing is then the mole ratio. And remember, we get the mole ratio from the balanced equation. And then finally we take the new moles, if you will, and convert to what is needed. Okay? We're following the same three steps. Back in Module 4, usually you would start with grams. So your first step was converting the grams to moles using the molar mass. The mole ratio, again, you get from the balanced equation. And then we usually were converting it back to grams. So we'd find the molar mass of the new substance and then convert it back to grams. We're doing the same three steps, but now what we're doing is either the first or third step is going to be substituted with the ideal gas law. So for an example, we may start off with the ideal gas law to get the moles, then we'll do a mole ratio and convert to what we need. Or we may have to start with grams, convert to moles, do the mole ratio, and then use the ideal gas law to figure out whether the volume, or usually the volume of the gas that we're dealing with. Okay, so it's again the same three steps we learned in Module 4. All we're doing is we're substituting either the first step or the third step with the ideal gas law. Now, which step you substitute simply depends on the information you're given. So let's look at an example to help us better understand what I was just saying there. All right, how many grams of sodium chloride can react with 18.3 liters of fluorine gas at 1.2 atmospheres at 299 Kelvin? All right, so they give you all the variables you need here to solve for moles using the ideal gas law. They give you the volume, they give you the temperature, they give you the pressure. When they give you all three of those, that should be the bell going off in your mind saying, I need to use the ideal gas law first, because they gave me all three of these. All right. Now they also give us the balanced equation. F2 plus 2NaCl yields Cl2 and 2NaF. Okay, and we have two F2s, two Fs, two NAs, two NAs. Remember that 2 distributes through, so there's 2 Cls and 2 Cl. So everything is balanced. Okay, that's our first thing. We got to make sure we got a balanced equation. And most of the time they usually will give you the balanced equation, but always make sure before you start. Okay, what do we have? Well, we got the volume, we got the pressure, we got the temperature, and we already know R because it's always the same. So that tells us that we have to use the ideal gas law first to solve for N. So we're going to use this formula and solve for N, right? Our first step in stoichiometry, figure out the moles. So when we plug that in, 1.2 atmospheres times the 18.3 liters, R times the temperature. And again, everything was already in the correct units for us. So when we do our math, we end up with 0.895 moles of F2. Now we've got the moles, we go to step 2 of stoichiometry, which is the mole ratio. Remember, to get this ratio, we have to look at the balanced equation. So let's slide back one slide here. All right, we are trying to determine the grams of NaCl reacting with fluorine. So this is the one we're looking for. This is the one we started with. When we do the ratio, we always take the coefficients. So the coefficient of the one we're looking for will always be on top, and the one we started with will always be on bottom. So the ratio here is 2 over 1. We're just taking the coefficients. Okay, so that's where this first ratio comes from here, this first conversion. 2 moles of NaCl over 1 mole of F2. We got moles of F2 on top and bottom, so they cancel out. The second conversion is the molar mass. Okay, remember back in Module 4, we want to get from moles to grams, we need the molar mass. We get this from looking up on the periodic table. We go to the periodic table, the mass of sodium is 22.99. The mass of chlorine is 35.45. So when we take those two numbers, and of course there's one of each of them, so all we got to do is add them together in this case. And that's where we get this 58.44 from. Alright, so again, it's grams per mole. Those are always the units for molar mass. So we're going to put the grams on top, the moles are on bottom. That way they cancel out the moles to get us the final answer in grams. Right, and again, we always set them up this way so that we just multiply by everything on top, divide by everything on the bottom. So we'd end up in this case with 105 grams of NaCl. Alright, so let's try one of these together. How many grams of sodium metal are needed to react completely with 17.8 liters of chlorine gas at 297 Kelvin and 1.25 atmospheres? So again, we are given all three variables, which tells us we got to use the ideal gas law first. All right, again, let's look at what we're given. All right, we are given the liters, so that's the volume. We're given Kelvin, which is the temperature. And we're given atmospheres, which is the pressure. R, again, is always the same, 0.0821, which means we have to solve for the number of moles, which makes sense, because again, that's always our first step. Figure out the number of moles. Now, before we do that, let's make sure that equation's balanced. We got 2 NAs on the left, and then 2 on the right. Cl2, and then again, that 2 distributes through, so we got 2 Cl's on the right, so everything is balanced. Alright, so we have N equals, and again we're going to have, and it is P times V over R times T. Okay, so our pressure, 1.25 atmospheres. Our volume, 17.8 liters. On the bottom, R, 0.0821. And the temperature is already in Kelvin, 297 Kelvin. Okay. Again, they may not always give them to you in the correct units. You may have to first convert them into the units you need before you plug into the formula. So make sure you always check those units also. Alright, so plug that all into your calculator. And we get 0.912 moles of chlorine gas. Okay, so that's our first step. Now we go to step 2, which is the mole ratio. So we look at the balanced equation, and remember, for the ratio we always want the one that we're looking for on top and the one that we started with on the bottom. So we're looking for the Na, how many grams of sodium. So we look up here, we've got 2 Na. The one we started with is a Cl. So there's 1 in front of that, so our ratio is 2 to 1. So that's what we're going to put down here. 2 moles of Na over 1 mole Cl2. Again, we do that so the Cl2s cancel out because we got 1 on top, 1 on bottom. Okay, so that's step 2. Step 3 is we now need to get to grams. So we're going to need the molar mass. And we go to the periodic table. And again, for sodium, the mass is 22.99 grams per mole. So we put the grams on top and the 1 mole on bottom. All right, so now these moles cancel with these moles, and then the moles of chlorine are canceled. So we multiply by everything on top, divide by everything on bottom. So 0.912 times 2 divided by 1 times 22.99 divided by 1. And that's going to get us 42.0 grams of sodium. Okay, so again, when they give you all 3 of these variables, volume, temperature, and pressure, that's got to be the bell going off in your mind saying I have to use the ideal gas law first, then the mole ratio, and then the molar mass. All right, now I also mentioned that we can do this with the ideal gas law at the 3rd step. So let's look at that scenario. All right, if you're asked to solve for volume or pressure, then we again take our ideal gas law formula and rearrange it. All right, we had again PV equals nRT. So if we're solving for pressure, then we divide both sides by the V, right? All right, if I'm solving for pressure, I divide both sides by V, and that's where I get this one from, nRT divided by V. If I'm solving for volume, then I divide both sides by the P, so I get nRT divided by P. So these again are just variations of the same formula, just depending on which one we're solving for. All right, so here's an example problem. If 52 grams of magnesium metal reacts with excess hydrochloric acid, how many liters of hydrogen gas can be produced at 27 degrees Celsius in 0.97 atmospheres? All right, so here, the bell in the mind thing, they gave me grams, and they only gave me 2 of those 3. I got pressure and temperature, but they never gave me volume. So again, there should be something going off in my mind telling me I need to use ideal gas law in the 3rd step because they only gave me 2 of these variables and they gave me grams. Okay, so again, make sure we jot down what we're given. We're starting with 52 grams of magnesium. All right, they gave us temperature, 27 degrees Celsius, and they gave us pressure, 0.97 atmospheres, and they're asking us to solve for volume. Okay, now before we go any farther, let's get things in the correct units. Remember I mentioned a moment ago that you always make sure you got things in the correct units. Well, degrees Celsius is not the correct unit. We made that in Kelvin. So if we add 273, that'll get us 300 Kelvin. And remember that conversion we learned back in lesson 5.03. Okay, atmospheres is the correct unit, so we're good with that one. All right, so now let's look at our balanced equation. We got 1 mg on the left, 1 on the right. 2 H's, H2, 2 times 1, 2 Cl's, and then 2 Cl's. So everything is balanced. Okay, so going back to the Module 4 type of stoichiometry, we have to take the grams that we're given and convert that to moles. So that's the same first step. We look up the molar mass. Molar mass of magnesium from the periodic table is 24.3. Because we're starting with grams, we need to divide by that number to cancel out the units to get us to moles of Mg. Step 2 is always the same, the mole ratio. So we go to our balanced equation. We're solving for the hydrogen gas. So that has a 1 as a coefficient. We started with the magnesium, which also has a 1 as a coefficient. So that is our ratio, 1 to 1. So over here we have 1 mole of H2 on top, 1 mole of Mg on the bottom. All right, so now the moles of Mg cancel out, giving us what we need, 2.14 moles of H2. Now for the third step is where we use the ideal gas law. We're asked to solve for volume. So if we go back a slide, we're using this first one here where we're going to take the number of moles times R times the temperature divided by the pressure. So we got the number of moles. R is always the same, 0.0821 times 300 Kelvin, and then divide all of that by 0.97, and you get an answer of 54.3 liters of hydrogen gas. All right, so let's try one together. If 45.8 grams of lithium metal react with excess water, how many liters of hydrogen gas will be produced at 27.5 degrees Celsius and 1.35 atmospheres? Okay, so again, they only give you 2. You do not have volume, so there should be a bell going off. They gave me grams, they didn't give me volume, so I must use the ideal gas law in the last step. Okay, so again, what am I given? 45.8 grams of lithium. I know the temperature is 27.5 degrees Celsius. I'm going to go ahead and add 273 to that because I know I want it in Kelvin. So I got 300.5 Kelvin. And the pressure, 1.35 atmospheres. Volume is what I'm looking for. And in this case, we are looking for the volume of hydrogen gas that is produced. All right, so first step, 45.8 grams of lithium. And we need to convert that to moles. So again, go between grams and moles. We need the molar mass. So we're going to go to our periodic table and look up the mass of lithium. And the mass of lithium is 6.94. Okay, and that will go on the bottom. Again, the reason for that is so we can cancel out units. We got 1 mole of lithium on the top. Step 2 is the mole ratio. Go to the balanced equation. We have a 1 in front of the H2, and we have a 2 in front of the lithium. So our ratio is going to be 1 to 2. So we have 1 mole of H2 over 2 moles of lithium. So 45.8 times 1 divided by 6.94 times 1 again, and then divided by 2. And that is going to give us 3.30 moles of H2 gas. All right, we are solving for volume. So we're going to use that ideal gas law. And again, we're going to rearrange it so we have volume equals something. All right, and on top, it's going to be N, which is 3.30 times R times the temperature, which is 300.5 Kelvin. And then we're going to put that over the pressure, which is 1.35 atmospheres. And plugging that all into our calculator, we get 60.3 liters of hydrogen gas. Okay, so again, the hard part really is to determine where you're using the ideal gas law. And it's based on what they give you. If they give you pressure, volume, and temperature, you use the ideal gas law first. If they only give you 2 of those and they give you the grams, then you use it last. All right, so at this point we're going to pause and have this be the end of part 1, and then we will come back with part 2 of this lesson in a moment. All right, welcome back to part 2 of lesson 5.04. In this one, we are now going to start looking at some other scenarios with the mole ratios and gases in chemical equations and things like that. All right, so first off, we're going to look at the mole ratios here. Okay, again, as we've been doing, the coefficients can also provide us with volume ratios, not just mole ratios, when they are at the same temperature and pressure. Okay, so as long as the pressure and temperature stays constant, then we can use the ratios for liters also. So a given volume of oxygen gas will react with twice the volume of carbon dioxide gas, meaning up here we have a ratio of 1 to 2 between the oxygen and the carbon monoxide. All right, so this only works for gaseous products. That's an important thing to remember. You can't do this with volume, or excuse me, with liquids or solids, but it does work with gases. So an example of that, the question asks you how many liters of propane, C3H4, need to combust with 3.8 liters of carbon dioxide, or excuse me, to produce 3.8 liters of carbon dioxide if all measurements are taken at the same temperature and pressure. Okay, now since we're starting with just liters, and the question is asking us for liters, we don't have to go through all the steps of stoichiometry. We can just look at the ratio. So we have 3 CO2 to 1 C3H8. So when we set this problem up, we have 3.8 liters of carbon dioxide, and we need to determine how many liters of the propane would be needed to make that happen. Okay, so we're just setting up a basic conversion here. And again, we want the one we're looking for on top. So it's going to be 1, in this case, liter of C3H8 over 3 liters of CO2. All right, so 3.8 divided by 3, and that gives us 1.3 liters of the propane. Okay, now again, that only works when you are starting with liters and you are asked to solve for liters. And again, it's important to remember it has to be at the same temperature and pressure. That's when we can do this. All right, anytime they start involving grams, then you do have to do the stoichiometry that we did in part 1 of this video. All right, the other thing is sometimes when they say the same temperature and pressure, they get really specific and say it's actually standard temperature and pressure. And back in 5.03, we did mention standard pressure occurs at sea level, and that value is 1 atmosphere. Standard temperature is defined as 0 degrees Celsius, which is 273.15 Kelvin. And again, sometimes, a lot of times, we just round that off to 273 and use that number. When you have any gas at standard temperature and pressure, then it occupies a volume of 22.4 liters. Okay, when you have 1 mole of that gas. All right, so let me say that again. If I have 1 mole of a gas at standard temperature and pressure, then it always occupies a volume of 22.4 liters. All right, this is called the molar volume. You may have read that in the lesson or heard that term before. This is called the molar volume. Now again, because that is an equality, just like molar mass, we can use it in conversions. Okay, but again, the key is we can only use it when we are at STP. Only when we're at STP. Any other time, we're going to have to go ahead and use the ideal gas law. But if the problem says we're at STP, then we can use the 22.4, the molar volume. Okay, so let's look at an example of that. Question asks, how many grams of calcium oxide would be produced when 50 liters of carbon dioxide is produced at STP? All right, so we are given 50 liters of the carbon dioxide. We need to figure out how many grams of the calcium carbonate are going to be needed, and it's at STP. It's at standard temperature and pressure. All right, well again, the first step of stoichiometry is always convert to moles. Well, because we're at STP, we don't have to use the ideal gas law. We could, it's going to get you the same answer, but it's a little quicker if we just go ahead and use the molar volume. All right, so that molar volume, 1 mole of CO2 will be on top, and the 22.4 liters would be on the bottom. Again, so we cancel out the units, right? Liters cancel out. Step 2 is the mole ratio. So if we go to the balanced equation, okay, let's make sure it's balanced first. I don't think we did that yet. 1 calcium and 1 calcium. 1 carbon, 1 carbon, 3 oxygens. We've got 1 oxygen there and 2 over here, so total there's 3 on the right side, so that is balanced. All right, so the one we're looking for has a coefficient of 1. The one we started with also has a coefficient of 1. So that is our ratio. 1 mole of calcium carbonate over 1 mole of carbon dioxide. All right, again, we put that carbon dioxide in the bottom so that the units cancel. Okay, now in the last step, to get to grams, we need the molar mass. So again, we go to our periodic table and look up the masses of each of these. Magnesium, or excuse me, not magnesium, calcium is 40.078. Carbon is 12.011. Oxygen is 15.99, but you have to multiply it by 3 because there's 3 of them in the formula. So you get a total of 100.059 grams of calcium carbonate per 1 mole of calcium carbonate. All right, so I'm going to go over here on the side just to recap that last step. On the periodic table, calcium has a mass of 40.078. There's only 1 in the formula, CaCO3, so that number stays 40.078. Carbon, off the periodic table, has a mass of 12.011. There's only 1 of those in the formula, so it stays 12.011. Oxygen has a mass of 15.99. There are 3 of those in the formula, so we gotta multiply it by 3. And that would give you 47.97. And then you just simply add those 3 together to get the grand total over here of 100.059. Alright, so again, we multiply by everything on top, divide by everything on the bottom. So 50 times 1 divided by 22.4 times 1 divided by 1, so that middle step really doesn't do anything there. And then we multiply by the 100.059, and then of course divided by the 1 again. And we end up with 223 grams of calcium carbonate. Okay, now again, the only time that you can do it this way is if it is at STP. Alright, since they said it's STP, we could use the molar volume. If it's not at STP, they will actually give you temperature and pressure readings, and then you got to go back and do it the way we did the very first problem in the part 1 video. Alright, lastly, we have diffusion and effusion. Very similar, but a little difference here. Diffusion is the gradual mixing of 2 gases because of the spontaneous random motion of their particles. In lesson 503, we talk about how if you're standing in a room and somebody's on the other end of the room and sprays a little perfume in the air, initially you don't smell the perfume. Maybe 30 seconds, a minute later, now you can smell the perfume. Well, you just experienced the process of diffusion. That gas is concentrated on one end of the room, that perfume, and as it's moving with the air particles, it will spread out until it fills the entire room evenly. That is diffusion. Effusion is similar in the sense that particles are moving from a place of high concentration to an area of low concentration. The difference is that they are traveling through a small opening in the container. All right, so say you have 2 containers side by side. Let's say, just for a simple example, let's say we take a couple soda bottles and put the mouth of the 2 soda bottles together, and in one of them we've been producing carbon dioxide gas. And when we put them together, that carbon dioxide gas is going to slowly work its way through the mouth of that tube, the mouth of the bottles, into the other one. Now, if I actually put a piece of tape over the mouth of the bottle and punctured a hole in it, so it was like a pinhole, and then did that same thing, now we have effusion because it's having to go through that little hole. Well, let's say I have two gases in that bottle. Let's say I have carbon dioxide and I have hydrogen gas. I have two gases in there. And I do that same thing. I have the tape over the end of the bottle, put a little pinhole in it, and then I hold the two bottles together so that the gases can effuse through the pinhole to the other side. Well, because we have two different gases, they're going to effuse at different rates. That relationship is called Graham's law. And the way they effuse is really based on how big they are. All right. The analogy here is, if you go to football practice, or any practice for that matter, but I like football, so we'll go with that. And you have a smaller guy versus one of those big linemen. Generally speaking, the little guy is able to run faster than the big guy because he has less mass. Well, the same thing works with molecules. The one with less mass is able to move more rapidly, so he gets through the pinhole quicker than the bigger one does. All right, so the rate of effusion of gas A, let's say the carbon dioxide in the example we were using, over the rate of effusion of the hydrogen, using that example, equals the inverse square of their molar masses. So we take the molar mass of the hydrogen and take the square root of that, and then we take the molar, and that's over the molar mass of the carbon dioxide, and then we take the square root of that. And all this does is shows us a comparison between the two. All right, it does not actually show us the rate of each of them necessarily, unless it gives us one of them, then we can figure out the other one. But it does give us a comparison between them. Now there are some variations to this formula, but they all really mean the same thing. Instead of rate, sometimes we talk about velocity. How fast are they moving? All right. And we can also use this for diffusion. Okay, so again, it's the same principle, same formula, just sometimes we modify it a little bit to talk about other things. Okay, so let's just do a couple practice problems with effusion. Let's say we have a sample of hydrogen gas and it effuses through a pourer 7.96 times faster than an unknown gas. What is the molar mass of the unknown gas? Okay, so like anything else, let's figure out what we got here. What have we been given? All right, we have been given hydrogen gas. All right, we know that is one gas, so we're going to need the molar mass of that. Now, if we go to the periodic table, we have 1.0079 for a mass. Again, there are two of them in H2, so we got to double that. All right, so we have 2.0158 grams per mole. We have an unknown gas, and they are asking us to find the molar mass for that unknown gas. All right, and then they tell us that it moves 7.96 times faster. Okay, now let's put up our formula here. Okay, now remember I mentioned a moment ago that that ratio is a comparison between the two. Okay, so over here we're going to have rate of hydrogen over rate of unknown. All right, and then over here we've got molar mass of the unknown. I'm going to abbreviate that. And on the bottom we have molar mass of hydrogen. Okay, and remember, we have to take the square root of each of those. Okay, now that 7.96, this is kind of the, I guess you'd say, tricky part of these, actually is the comparison between these two rates. So this part here, 7.96, plugs in for this whole expression here on the left, because it is the comparison of the two. All right, whenever it says times faster, that's the indication that you have the entire expression there. Okay, so that means we're going to have 7.96 equals. Okay, now we got to plug in the other info. All right, we're going to take the square root of the unknown, and then on the bottom we have the square root of the molar mass of the H2O, which we already figured out from our periodic table, is 158 grams per mole. And then up here, we'll just put in an X, right? Just like in math, for the one that we're looking for. Okay? Now, I'm sure you probably know in math, to get rid of the square root signs, we have to square it. Okay, but if we're going to square this side, we also have to square the left side. Right? That's just a principle for math, right? If I square one side of my equation, I got to square the other side. Okay, so I got 7.96 squared. That's going to give me 63.3616 equals okay, on this side then, we now have on the top we have X grams per mole, and then on the bottom we have 2.0158 grams per mole. Right? We just got rid of the square root signs by squaring everything. So of course, to get X by itself, we need to multiply both sides by the 2.015, right? So when we multiply both sides by that, X will give us 127.7 grams per mole. Now, a nice easy way to kind of do a self-check here. Remember we said that the lighter molecule moves faster. Well, this molecule is 2.015 grams per mole. This one is 127.7. So would it make sense that this one up here can travel almost 8 times faster than this one down here? And the answer to that would be yes. Right? The lighter molecule will travel faster than the larger molecule. So our answer at least makes sense when we compare those two together. All right. Now another type of problem you'll come across is it may just say, well, which of these gases is going to move faster or effuse faster under the same temperature and pressure? Well, to do that, we just need to look up the molar masses. So we look up the mass of carbon, and the hydrogens. And the molar mass of CH4. All right, you got 1 carbon, 4 hydrogens. Yeah, add their masses all up together, you get 16.04 grams per mole. All right, for chlorine, I'm going to put this one above it so we can kind of space them out a little bit here. Chlorine's mass is 35.45, and we got to double that for Cl2. So we've got 70.91 grams per mole. For O2, 15.99 times 2, 31.98 grams per mole. And then finally neon is 20.18 grams per mole. Okay, so we got to look at the molar masses. That's how we always compare them. And then the question again asked us which will effuse the fastest under same temperature and pressure. So we got CH4 with 16, chlorine is basically 71, oxygen's basically 32, neon's 20. Well, out of the 4, the lightest gas is CH4. So CH4 would effuse the fastest. Neon would be not too far behind. Then oxygen, and the slowest one in this case would be the chlorine. All right, so it's just looking up the molar masses and then comparing the 4. All right, so what's next? Well, you have now gone through all of 5.04. Make sure you go back and read through the lesson, complete all examples and practice problems. If you're still needing some help after that, you can attend the open tutoring session. You can also use the lesson reviews found in the Student Resource Center. And then when you're all done and you feel comfortable with the material, you can go to the Assessments tab or the Gradebook tab and complete the 5.04 quiz. I hope this was helpful, and we look forward to seeing you again.